and thanks for welcoming me. So during this talk, I will speak about OCaml, or inlining work in the compiler, and what we can do to interact with inlining. Either like to check that inlining has been done, or just when we want inlining to be done. The first part, I just give a short intro to the OCaml compiler so that we just more or less know where I'm at in the compiler and what I'm talking about, and basically all the compiler work. Because inlining is an optimization inside the compiler that interacts with other part of the compiler. So OCaml, like basically any compiler, has a lot of different intermediate representation. We can split them into three big categories: front-end, middle-end, and back-end. Get a source file that you want to compile, you first parse it, and then you type it, and that's basically called the front end. And at the end of the front end, you got, not working. You got the lambda IR, and this IR is really when serious things start to happen. So in the lambda IR, you lose any information about modules, about functors, just for those who are not aware, functors are functions that take a module as parameter and return another module. So all of that doesn't exist anymore. You also already know that your code is type checked, meaning that typing, like any things related to typing, just disappear. So in OCaml, you got records, which are just a bunch of values merged together, each with their own label. At this stage, we don't have that anymore. The only thing we got is values in what we call the OCaml memory representation of values, meaning you got a tag, and then you got a sequence of things, which are either constant or a pointer to another OCaml value. So starting from lambda, we reach what we call the middle end. The middle end is what we are going to be interested in today, and that's where inlining happens. And every inlining and other sort of high-level optimizations. So maybe a bit of unboxing, maybe a bit of loop unrolling, maybe a bit of loopification. But for our purpose, we will mostly be interested into inlining. So as you can see in these slides, we got three different representations for the middle end: C lambda, F lambda, and F lambda 2. They are all three different optimization engines. For historical purpose, they are all different. So historically, C lambda, or so we name it Closure, was the first one, and it's really fast. It generates code that works, but is not like the most incredibly performant code. And so I think around 10 years ago, work has been done to create F lambda, maybe a bit less than 10 years ago, which was meant to be a super good inliner to do a lot of optimizations, maybe a bit too much. It's sometimes a bit too aggressive and hard to keep under checks. And so in the past, I think 5 years, we at Giant Street and some other people have been working on F lambda 2, which is meant to be the successor to F lambda 1. We learned a lot from F lambda 1, and the goal is to have something that is more flexible to improve as time passes and to implement new optimization on top of. So middle end stops at the CMM representation, which is the last one that is completely architecture independent. So it's already looking quite like assembly. There's a bit of instruction selection, but mostly this representation is really suitable when you want to lower down to assembly. For the rest of the talk, I'll mostly interest myself on the native code compiler. So there's also a bytecode compiler, but we're not interested in that one. And then there's the backend where we got other representations. We do a bit of constant sub-expression elimination. We do a bit of instruction scheduling, register allocation, basic block layouting, a lot of things. And in the end, we just generate assembly code. And all of that is included in the compiler. We don't use LLVM or anything like that. So if you were right now to install an OCaml compiler, it's most likely that you will go through this intermediate representation. So you are going to use the C lambda intermediate representation, and then you are going to use other IRs. In this talk, I'll assume that we are going through this step. So we don't really care about the front end, we don't really care about the back end, but what we mostly care about is that we are going through F lambda 2. The inlining heuristics I'm going to present are extremely similar between F lambda 1 and F lambda 2. There's a part where they are, that I'll tell you about, where they are a bit different, but I'll explain when we get there. Lastly, before jumping to inlining, I just want to highlight how the OCaml deals with different compiling files that are depending with each other. So basically, every time we want to compile a file, for example, test.oml, the compiler will generate at least 3 files. The first one is an object file. that contains the binary code. Then you also got two artifacts, which we call the CMX and the CMI. The CMI stored typing information for this module. So whenever, like, if tests were depending on two modules A and B, if we were to call a function defined on A or B, the compiler would load the CMI file to get that information and do the typing. And a bit similar to the CMI file, the CMX file is either, but will add information about the implementation of your functions. So whenever we want to export a function for inlining, that's where we are going to put some information about it in the file. And so it's important to keep in mind that these files are, like, the more information we put in this file, the larger the file grows, so the most time the compiler must spend serializing them to disk, but also reading them whenever it needs. And so that's more work, and that's a slower compiler, and we need to reach a balance about what gets put into the CMX file versus what doesn't. Now, inlining. Just a small recap about what is inlining. So here we get, okay. No, still not working. So we get, well. So, no, that's fine. No, okay. So yeah, the problem is always between the keyboard and the chair and the keyboard. So we define a function foo, and we call foo, but when we call it, we have information about the arguments. And so inlining in the regular sense of the term is like, you take this call, and you take the body of a function you want to call, and then you are just gonna put it, replace it. And yeah, that's it. So you don't call, you don't branch somewhere in the code that your CPU is not aware of, but you increase the binary size. We are mostly interested into inlining because, so we still don't make the call, we still like go a bit faster, but mostly like now that we got more information, like we knew that this B was true, and we knew that X was 45. So with that, we can do some more optimization and reach a very simple expression that we weren't able to before. So inlining is mostly interesting for other things. So for example, inlining can allow us to remove allocations. So here we got a function that will create a tuple, and then we just gonna call another function of the result, which just take the first element. So once we inline tuple and first, we can just entirely not allocate this tuple. I got nothing against allocations. OCaml is garbage collected. Most allocations are actually quite fast when you first allocate. It's just that later on down the road, the GC will eat, and then you will take a latency hit. And when you want to write performance-sensitive code, that's bad, because the first thing you want is for your performance to be deterministic. The second kind of things that we like about inlining is that we got high-level order constructs. So you can create a function and pass to it another functions and then call this function. If you're not careful, you will there have an indirect call, and we don't like indirect calls. The first reason why is that the CPU doesn't like them, because it's very hard to predict where an indirect call leads. So every time you see, like, you execute code, you've got an indirect call, the CPU must wait to know where it goes from, and it can't go as fast as it would go otherwise. And the second is just some very OCaml-specific stuff, because we execute a lot of boilerplate every time we execute an indirect call, because we need to know if a function was totally applied or not. And so we want to avoid indirect call as much as we can. So in that case, inlining indirect allows us to replace f by integer addition, and just have also some very simple body. So just in summary, OCaml is about functional programming. We got a lot of high-level constructs that needs inlining to be compiled efficiently, like especially functors. Like you just take a pack of functions, you then create another pack of functions, and if you're not careful, that's indirect calls everywhere. The second reason why we love inlining is that it's a way to trigger over-optimizations that would be otherwise really, really hard to implement. One example is unboxing. The other is just transforming direct calls to indirect calls. Lastly, for the inliner, we need to keep in mind two things. The first one is that we'd like an inliner that is quite easy to understand when you're a user. And like, so every decision, like, you shouldn't ever be surprised by the inliner, but also like everything that the inliner does should be able to be explained. And the last part is that we don't want to have slow compile times. We want our compile times to still remain quite fast. Not extremely fast, but like fairly efficient. Now, in the language, the first thing we got on the inliner is annotations. So there's three main kinds of annotations. The first one is on the function definition. You can say that this function needs to get inline every time you call it. The other time, you can say, oh, I don't want to inline it. And the last thing is on the code side to say, I really want G to get inlined. These annotations, the compiler is trying really hard to always respect these annotations. If they are not, it will emit an error. And we kind of like these annotations because whenever we see in the code that something was annotated, it gives us a bit more context about this code. So if I'm seeing a function that was annotated in another ways, I can tell to myself, oh, this is performance-sensitive stuff. I need to be aware about what's happening. And it also provides stability between words of the compilers. Now a small break, just a very high-level intro to heuristics. I will not go any deeper than that because that's not the talk for it. So the main primitive of heuristics is a function called simplify that takes an environment, and in this environment are stored information about everything that we encountered. It also takes the expression that we want to simplify. And it will return two things: a new environment, which can contain more information, but also statistics about the code being simplified, and a function that, when called, will build the simplified version of the expression. So when we call simplify, we go down the expression, we traverse it from top to bottom, we construct a set of instructions about how we should simplify this expression, and then once we reach the bottom of the expression, we just turn around and go back up. And while going back up, we adjust our instructions to have a very clear idea about what will be the simplified expression. We can build this simplified expression, or we cannot build it if we are only interested about certain properties that it will have. So one other thing that is at the core of Inliner is what we call the code size approximation. So this is a metric that takes as input an heuristics expression, and the only goal of it is to approximate the size of a binary code that would have been emitted. We are actually not compiling it down to binary to take the real size, because that would be way too slow. Instead, we're using a very, very crude approximation that we can compute incrementally. Just to give you a few examples, whenever we got an let x is equal to x1 in x2, the size of that, the approximation, would be the sum, the addition of the two. For a match statement, at this point, patterns have already been compiled, so we can only jump to integer tags. The size would be 5 times the number of bunches, plus the sum of the size of every single sub-expressions. And lastly, we also got some constants. So when we want to do a direct calls, here x is an identifier, so it has no size. We just say that it's the constant 4 for indirect calls, is the constant 6. And lastly, for primitives, which are basically a call to integer addition, bitwise operator, we just have constants that depend on the operators. All of these constants were created by looking at the assembly output and trying to make a best guess. And really, the goal of this code size approximation is to be more or less correlated with the size of a binary output, but also to be comparable between two different approximations. We don't really need it to be super, super precise. The inlining heuristics will work on two steps. The first step that occurs is on function definition. When we see a function, we look at the body, and we optimize it. And we also compute its code size. And then we will classify this function into 3 different parts. Ever if its code size is below a threshold, we say that it's small, and in this case we are always going to inline it. If its function, the body is very large, we are saying it's large, it's over a given threshold. We are saying that it's not to be inline, never to be inline. In that case, we don't put any information about it in the CMX file. If it's in the middle, we still put information about it in the CMX file, meaning that it will be available for inlining. And in that case, we say that it's speculatively inlineable, and we'll later on take the decision to inline it or not. In the case of an attribute, we just say that the small function threshold is really, really high, so it's always getting exported. Functors are dealt a bit specifically, because functors are large, so we just say that they are always going to get available for further inlining. Now, whenever we see a call to a function, we first look at its implementation. We get it in the environment. And then we look at how it was classified. If it's classified to be always inlineable, we always inline it. If we got a body, it means that we might inline it, and so now we need to take the decision. So for that, we're going to take the function body and take all of the information we got about the arguments. So information about the arguments can be like, oh, we know the value of argument, but it can also be something like we know the shape that this value will have. Like we know that it's a tuple, or we know that it can only be, like we got a sum types, and we know that it can only be one of these two sums. And we take all of that information, we build an optimization environment for it, we pass the body, and we call simplify on it. And while we simplify, we are going to keep track of two things: the code size approximation of a simplified code, and also the number of removed operations that we would have executed if we were to call this function. So we are going to keep track of a number of polymorphic comparison, indirect codes, allocations, primitive, and branches. So in that case, I'm starting to simplify, and I see that B is 1, and so this check is always going to be true. So I can remove that, which is a polymorphic comparison, but I can also remove a branch that I don't need to execute. So I'm removing a branch, and I'm not generating any code right now, so like code size is still 0. Now I'm inspecting, and I saw that x plus 2 can be simplified to 47. So that's a code size of 1, because I'm creating a constant, but I also removed the primitive call to the integer addition. Now I'm looking at big function, and I'm taking like this information from whatever it's defined. I'm seeing that it's speculatively inlineable, and because I'm already speculating, I will not go any further to try to inline it. So whenever we do speculative inlining, we don't recurse to do over speculative inlining. And so this big function, we still have a call, which has a cost of 4. And we can go on and then optimize the indirect call to f, which make us one less indirect call, maybe inline a second, and then see that we can remove one allocations. And so in the end, we are just left with a call to big function with argument 47, which has a code size of 5 and removed one operation of each category. Once that's done, and we've got this metric, we're going to plug them into these formulas. The first one is to compute a score for all the removed operation, which is basically element-wise a cross product of all of the vectors of removed operation with some costs, different costs that are all hyperparameters. And we are going to inline only if the code size we measured minus this cost of removing all of this operation is less than a threshold, which is another inline hyperparameter. So in that case, we decided that foo could be inline, and we construct the body and replace it with a function body, and we got big function of 47. And until now, these heuristics are also the one that are used inside f-lambda1. Now there's a global backstop to avoid inlining forever, because you got a big inlining chain. It's actually like really hard to control how much inlining you are gonna do, because people can write funny things like the Y combinator, which is not really recursive, it's just something odd that you could inline forever. So we still design this backstop to be set quite high. I think it's set to either 10 or 50 or something like that. So if, for example, we were defining it to be 4 and we want to inline the F8, we could only inline it up to F4 and not any further than that. And so now, when inlining goes a bit bad is when you got multiple compilation units, because you've got a lot of state to share and a lot of environment to share between units. And that's where f-lambda2 is an improvement over f-lambda1. The first tricky scenario that can happen is with this inlining depth scenario. So here I got two files that are both compiled with a maximum inlining depth of 3. I'll get them simplified under two scenarios. The first one, where we will decide that when defining F3, F2 should be inline. And the other one where we don't. Now, once we are compiling B, we'll maybe decide, oh, G1, we are going to inline that. That makes 2 call to A.F3 appear. And now we might say, yeah, A3 was marked as can be inlined, so I'm going to into be inline it. So I'm going to retrieve the body from the other compilation unit. In that case, that would be F1. And so I'm going to plug F1 there. And in the other case, it was F2. And now I've inlined already twice in these files, so I can inline once more. In one case, I got a call to F0. In the other one, a call to F1. I claim that this is quite bad, because it means that if you move your function across compilation unit, you might generate different code. And you can't really know about that in advance. It's confusing for the user. It's more work for the inliner that we shouldn't be able to do. It's very hard to control. So what we are going to do is store on every apply node the depth where it was first created. So we start by setting it to 0 everywhere. And so when we inline F1 and F3, it's inlining depth 1. So now we continue. We inline once, we make every node was created with a depth of 1. Now we inline another time, so that's a depth of 2. Here what happened is that I inline a second time, A3, so it was a depth of 1, but I'm also looking at the depth that was marked on this part, which was 1, and I'm doing the sum of the two. So that's 3, and that tells the inliner you can't inline that any further. And we can keep in bound the inlining chains like that. The second part that is quite tricky is what's going on with hyperparameters. We got a tons of them. So there's the maximum inlining depth. There's the different function thresholds. There's the different constants for remove benefits. And we want the user to be able to customize them because they directly compile time units, and maybe they want like one file, they know that these parameters are going to be the best because they want to emphasize on removing more indirect calls. So we want to be able to compile different compilation units with different hyperparameters while still having some sane behavior in the middle. One example, 2 files, 2 different inlining depth. So B will very shallow inlined. That means for us, it means that in B, when user compile B, they don't really care about the performance of any code coming from B. It's not really performance sensitive. So we shouldn't export more information than necessary. And B, A, which is compiled with a bigger inlining depth. So we could say, oh, I'm inlining foo, that makes bar appear. And there I'm going to inline b.foo, that makes a call to b.bar appear. And then maybe I can inline it a bit further and make fuzz appear. And that has an inlining depth of 2. But this thing, like in b.ml, we say that B can only be compiled with a maximum inlining depth of 1. So that's quite bad, because we just went to export more information from B that was required to. And the correct behavior is just to stop inlining. So like previously, we're going to store more information on function definition on apply nodes. And this information will be the set of hyperparameter used, which can be compressed quite nicely because most of the time you only want to use a 1 or 2 or 3. And so we got some good sharing. And so whenever we import code from another compilation unit, we say that this code will only be optimized using the weakest optimization settings between the current file and the compilation unit it was coming from. So in this case, we stop at foo. Okay, so now we went through all of the inlining heuristics. There's a question of visualizing inlining. That's actually quite of a hard problem because inlining moves a lot of code. Some code that you are moving will be generating some assembly that looks nothing alike. You can ask questions like, is this function inline? Is this function not inline? Why? And also, like, it's critical to performance. And you don't really want regression, or at least you want to be able to explain them, to explain why something changed. And that's happening quite frequently. So I think last week someone came to me and said, yeah, why is this thing not inline anymore? Like, it's now allocating. We didn't wanted that. Just answering some question like, who am I calling is quite hard. So here's, I'm creating a function called author that inside it will create another function called inner and then called inner. We can assume that this is not going to be inline there. And then I'm calling author with no information and with some information. So with that surprise, we're going to inline the other one. We inline it, and now we got 2 calls to inner. But are they really calling the same inner? Like the implementation are definitely different. It may seem so if you're looking at the file itself, but implementation-wise, it's not really the case. So we need to show that to the user. So we've introduced a representation called the inlining tree that will record every single decision and put them into a tree format. So here's a simple example. We got 2 functions, 2 that just calls to something else, and another one that creates a function that calls to something else and then calls this function. When we first optimize F2, we are going to store a node in this tree about that, the information that we define F2, and then that F2 is calling F1. On every of this node, that is not being shown that is attached an inline decision. Otherwise, it will make the slides a bit too cramped. And we can do the same with F3. Now, when we inspect F4, we create a node to show that we decided to define the function F4. We define another function called F5 that calls F3. At this point, we might say, hey, I can inline F3. And so we create a new node that is another function called to F2. So we got a call to F3 that now leads to a call to F2. That means that this call has been inlined in the tree. I can now see I'm calling F5. okay, so I'm calling F5, I might inline F5, and because when I first define F5, I have inline F3, and then there's a call to F2, so all of that still happens. But the decision to inline this F3 was not taken while compiling this function. It was taken while first defining F5. So I'm adding an edge to represent this idea. And then finally, I can also say F2, I'm going to inline it. And I'm showing that in this tree representation. Once again, not once again, but every apply node have an edge to the function that, okay, this edge, yeah, this is bad, but have a node to the function it was calling in the first time. Now, constructing this inlining tree is a two-step process. The first thing we are going to do is collect what we call relative histories on function body and apply nodes. So these histories are relative to the previous node that is considered for inlining. And then every time we see a function definition or an apply node in the inliner, we are going to store the decisions. So for example, while compiling the definition of author, I'm going to say, oh, there's the top level, and then this one is the definition of author. This one is the definition of inner, and this one is a call to the function that was designed from the top level, then going to the definition of author, and going to the definition of inner. And because I made decision on every of these things, I'm storing a path, absolute from the top level, about this decision. Usually, we do that always. We compute the relative histories always when we compile, and only when we're interested in knowing information about a file, we're going to compute all of this. We are going to record all of this information. Now I'm calling author. I'm not inlining it, so I'm just inserting the thing that I've called a function, a call to a function defined at the top level named author. Then the other one, I'm calling it. Now I decide it's inlined, so I'm going to extract this body and put it there. And for every single one of this relative history, I'm going to prepend it with a relative history of this call. Meaning, like, I called the function author defined at top level, decided to inline it, and that yielded a definition of a new function inner. So there's some history related to this thing. And finally, I've got this call inner, which is also appearing after inlining the call to author, but this time we are calling the function inner generated after inlining author. And so from all of this, we can merge them and to build a tree. And now that was the first motivational example. And we can see that this function inner that we're calling after inlining is not the same one as the one that was called on the other location. So at this point, that's great. We got an inlining tree. We still need to do something with it and to show it to the user. So it's a tree. We could either like put in a graph format, put it in a file and give that to the user, but that's actually not super helpful. So we took a step back and we looked at this. So I don't know if you're aware what it is, but it's a website. You can put some snippet of code and that generate the assembly, and then you've got colors to tell you, oh, that's this thing, that's this thing. And it's quite nice because it's interactive and you got visual information. The only thing that I don't quite like about it is that, first of all, it's not exactly working on a big code base. You need to have a small example. And the second thing is that most of the time, you don't really care about assembly. Like, I can't read assembly. And when I'm looking at assembly, it's only to know something about the code being generated. So maybe I want to know if something is allocating. Maybe I want to know if something is inline, but it's not really clear there. Or at least not clear if you don't have expert knowledge. So what we want is to extract information from the compiler and then put it over your source file. So we built a plugin that sits between our build system, between the compiler, and between an editor. We got the source file, so this is extracted from Merlin, which is a tool widely used by OCaml developers. And we can ask about everything that gets inline into this file. So in orange are things that we are inlining, and in red, pink or purple are things that are not going to be inlined. And then we can ask, like, why was string.uncapitalized inlined? And that will open a buffer showing to us what happened. Like, we inlined it because it was small. Maybe it's more interesting to understand why try-file wasn't inlined. So we get a lot of information, and we also get like some information about the body of inline, as it was considered by the inliner at that time. So all of this information is telling us that it has not been inlined, but still we speculated on it. So we can look a bit further to know why we didn't achieve the the desired code file, code size optimization. So we can take a look at the canonicalized file name, which wasn't inline. Okay, the explanation is not really good, but it wasn't inline because the environment says so, apparently. And now, more interesting, if we come back and we look at exact file exist. So this is blue, and this means that the decision to inline misc.exact file exist was taken not while doing speculative inlining, but while we first compiled the function twi file. So if we click on this thing, we go back to the context where we first defined twi file, and we can see, yeah, this was inline, and I can now look and ask questions about why was it inline. It was inline because it was small. And like that, we can traverse the inlining tree visually and interactively. And when the code refreshes, we got some, when we make a change to the code, the buffers gets updated. And it's quite nice to use. So in conclusion, the three main takeaway of the talk is that in OCaml, inlining is important, but we don't have overly complex inlining heuristics. Because in practice, like, we still got a very small time budget to work around when we do inlining. The second part is that inlining is tricky. So you need to be super careful when you do inlining, especially when you inline across compilation units. And the second is that a compiler doesn't need to be a black box. Like, it's just another tool in your tool chain. And so the first thing is that you should be able to control it. Like, maybe the user is saying to inline a function, and that's a bad idea. But the user decided to. And it's not exactly the compiler place to say, oh, that's bad. Like, I want to generate suboptimal code, let me do it. And also, we should be able to give feedback to the user about what optimization trigger, especially when they are quite important to the end performance of your code. So if you got any questions, feel free.
Yes, thank you for your talk. Any questions from the room? In the meantime, I will also check the Discord. And I also do have a question. So earlier in your talk, you showed these annotations where you can give hints to the compiler whether you want something to be inlined or not inlined, and you can do this at the function definition or at the call site. Do you always have to give this, or can the compiler decide on its own? Like, if a function is not annotated as to be inlined, but the compiler sees that it's small and maybe it should be inlined, can it do it on its own, or?
So that going back a lot. So that's part of actually when you first define the function, you classify its body, and then you give a status to this function definition. If it was very small, it's the same as using an always inline attribute. You're always gonna inline it. So yes, the compiler can. What we can't do yet is take some numbers from real run and then translate them to annotations.
Thank you. Let me check the Discord. I think Jules is typing, so maybe he'll have one question. Any questions from the room in the meantime?
I guess since you've implemented and deployed this, I wonder if you've, from feedback from developers, if this has affected their behavior, if they sort of are able to understand more what's going on and are using these features and sort of thinking more about inlining, and is this helpful for them as a kind of tool for understanding? Because inlining is historically, very opaque. It's a magic thing that you don't think about. Are developers sort of positively responding and maybe having some better behaviors in how they use these user-supplied annotations than they did before you rolled out this visualization tool?
So the answer will disappoint you, but not exactly. We're still in the process of rolling out from that tool. So this is still a pretty niche thing that only a few people can use. What, however, we've had great success with is using the same methodology, but to highlight every part of the code that is allocating and explaining why it's allocating. So not for inlining, but for other stuff, yes.
that, I wonder about the kind of budget you have for visual noise in IDEs and stuff, right? Is this?
So this is an opt-in. It's a command that you run that will give you that, and you can toggle it off. So you only turn it on when you want information about that.
Thanks.
Meantime, also a question by Jules. Nice talk. Speaking of giving feedback to the user, is there a way to see how well inlining a function performed? So, for example, I have a feeling it would be good to inline foo. So I write foo at inline always. Then I'd love to see some info about what effect that had.
No, that's a good point. We don't have an easy way right now. The easiest way would be to make the change, recompile it, and then compare the two reports that the compiler gave.
Okay, thank you. And also an obligatory question by Jules. F-lambda2 in OCaml when?
We are currently testing it in production. And so the point, I think, is to wait for OCaml5 to stabilize and then start discussing a bit more actively with upstream about an upstreaming plan. So not until a year or two.
Okay, thank you. So I think if there's no more questions, then thank you again for the talk. And